It's 1974, and an Australian professor at the University of Melbourne, Richard Robson, is preparing for what should be an ordinary chemistry class. Today's topic is molecular structures. To help his students visualize how atoms connect, Robson is building human-sized models. Wooden balls with holes drilled into them to represent atoms, joined together by rods that stand for chemical bonds. Halfway through assembling one of these models, Robson stops. Staring at these oversized molecules, he realizes something strange. If atoms can be treated as building blocks that snap together in predictable ways, why couldn't molecules themselves be built the same way? That single question would eventually help create an entirely new class of materials. One so customizable that chemists could design matter almost atom by atom, and so impactful that Robson would be one of the 3 scientists awarded the latest Nobel Chemistry Prize. Before Robson's discovery, chemists already knew how to create some molecules. Take salt as a simple example. If you boil seawater until all the water evaporates, you're left with sodium chloride, a crystal made of positively charged sodium ions and negatively charged chlorine ions, locked together in a repeating pattern. This kind of process is called self-assembly. The molecules naturally arrange themselves into the most stable structure possible, without much human guidance needed. And this approach worked, but only up to a point. The problem was control. Chemists could make materials, but they couldn't precisely design their internal structure. Pore size and internal geometry were mostly accidents of chemistry rather than intentional design choices. That lack of control became a serious problem when scientists wanted materials with very specific internal features. Imagine designing a material that captures carbon dioxide from the air. The pores would need to be exactly the right size, just large enough for CO2, but too small for other gases. And the interior would need to chemically favor CO2, so it stays trapped. But chemists had no reliable way to build materials with pores of predetermined size or shape. Creating a certain material configuration was largely a matter of luck, not design. This is where Robson came in and transformed the field of chemistry. He realized that just as atoms form molecular geometries, molecules themselves can form predictable compound geometries. By using metal atoms as the wooden balls, and carbon-based molecular chains as the wooden sticks, linking the metal atoms together, Robson described a way to create a whole new class of materials called metal organic frameworks, or MOFs. This new material allowed scientists to engineer pore size, molecular shapes, and chemical environments with unmatched customizability. He was the guy who gave scientists the materials they needed by providing a theoretical framework of how to create compounds with specific properties. But soon after his success, disaster struck. His idea was simple in principle. Metal atoms act as connection points. Organic molecules act as linkers, and geometry dictates their final structure. The theory worked beautifully. The experiments did not. For years, Robson fought to build molecules, but he kept failing, over and over. Early MOFs collapsed as soon as chemists tried to use them. The pores, which should have cathedral-like space for chemicals to react, collapsed under their own weight. MOFs were fragile, inconsistent, and hard to reproduce. Many members of the chemistry scientific community dismissed MOFs as an idea that could never survive real-world conditions. But Robson never renounced his idea, and continued publishing MOF research throughout the 1990s. However, Robson's research group was small and underfunded. He was never able to stabilize MOFs. It would take a new generation of research to turn Robson's theoretical dreams into a practical reality. MOF research would turn stale for a few years, with no major conceptual leaps being made. That is, until 2003, when Professor Susumu Kitagawa from the University of Kyoto in Japan published a groundbreaking paper. You see, Kitagawa didn't see MOF collapse as a failure. he viewed it as an opportunity. You see, Robson's MOFs were considered fragile for two fundamental reasons. First, the metal ligand bonds. These bonds were strong enough to crystallize the structure together, but weak enough to bend, rotate, or elongate when exposed to new environments. More like a paperclip than steel. Second, the organic atoms linking the molecule together didn't behave like rigid beams. They acted more like hinges, allowing the entire structure to rotate and tilt. However, Kitagawa completely reframed how MOFs were understood by interpreting this weakness as a superpower. He realized that MOFs were capable of forming multiple possible crystal structures. Which structure appeared depended on the energy of the surrounding environment. And critically, these transformations could happen without destroying the molecule. The crystal's intrinsic pattern and purity were preserved, meaning transitions between states didn't necessarily cause collapse. What was once considered fragile, weak, and collapsible began to be viewed as mobile and dynamic. He showed that MOFs could switch between a dense, hard, non-porous material and a porous, open structure simply by being introduced to a specific atmosphere. MOFs were no longer intended to be these concrete, open space cathedrals. They became something more complicated, a material that could adapt and change its shape almost as if it was alive. And he would later become the second of the 3 scientists awarded the latest Nobel Prize in chemistry. However, a critical problem was still bubbling under the surface. MOFs were not yet customizable in the way Robson had theoretically predicted. Researchers still couldn't say, I want this pore size, with this geometric structure and this level of stability. Instead, every specific MOF had to be studied in detail before being put to use. The creation of MOFs was still nothing more than an educated guess. There were simply too many interconnected variables at play, and no way to control one without disrupting the others. MOF research hit yet another roadblock. Because for years, scientists couldn't answer this one critical question. How do you turn practical MOF design from a guessing game into an architectural system? This is where the third Nobel Prize winner makes his appearance. Professor Omar Yaghi from the University of California, Berkeley. While Robson laid the theoretical groundwork for MOFs, and Kitagawa made them dynamic and mobile, Yaghi laid the groundwork for their architectural design, allowing strong, dynamic MOFs with specific properties to be designed at will. He did this by replacing the single metal atoms inside MOFs with metallic clusters. Unlike a single metal atom, every metallic cluster had a specific geometry, with a fixed number of chemical bonds and fixed bond angles. This meant researchers could finally control MOF geometry by choosing a particular cluster. Metal atoms have many connection options. Metallic clusters only have one. That predictability changed everything. Yaghi made the same shift with organic linkers, the second critical component of MOFs. Previously, MOFs were created using flexible, string-like molecular linkers, which could bind in unpredictable ways. Yaghi replaced these with stiff, rigid, bar-like linkers that behaved exactly as intended. For the first time, MOF structures could be designed on a computer. And just as Robson had imagined during his classroom lecture all those years ago, wooden balls could finally represent metallic clusters, while the beams could represent organic linkers. His dream came true. This architectural approach to molecular design became known as reticular chemistry, chemistry that follows the rules of networks and rarely deviates from its intended structure. Together, Robson, Kitagawa, and Yaghi invented, refined, and ultimately formalized metal organic frameworks. Today, researchers all around the world are using their creation to tackle problems within numerous fields, from biomedicine and drug delivery to water purification and energy storage. Most importantly, scientists are exploring MOFs as a way to capture greenhouse gases like CO2, one of the main drivers of global warming. As of right now, MOFs can already capture extraordinary amounts of CO2. A single gram of a material known as MOF 74 can have a surface area larger than a football field, with tons of locations for CO2 to be trapped. Now, researchers are combining AI-optimized MOF design with reticular chemistry to scale this process up, with the goal of reducing the amount of carbon in our atmosphere. If you're interested in learning more, I've linked sources below. And if you want more stories like this from the frontier of science, subscribe.